Hello everyone. Let's continue solving the problems of the third chapter, problem 3. An actuator system is shown in this figure. Here you can see the structure of the actuator system. This is the stationary part and we have this coil on it, and this is the moving part. We generated the model of this structure in the ANSYS Maxwell software. Okay, so in this video, we are going to solve the problem analytically, also using the ANSYS Maxwell software, and compare results. All the dimensions are in centimeters. The magnetic material is cast steel, whose magnetization characteristic is shown in this figure. Yes, we have this figure from the chapter 1, and the magnetic material of the core is the cast steel. We should use this curve, right, for our calculations. The magnetic core and air gap have a square cross-sectional area. The depth of the problem is not given here, but because the cross-section is a square and the width of this vertical limb is 5, this horizontal limb is 5. So the depth of the problem is also 5 centimeters. The coil has 500 turns and 4 ohms resistance. The number of turns and the resistance of the coil are also given here. A. The air gap is 1 millimeter. So if the length of the air gap be 1 millimeter, determine the coil current and supply voltage DC required to establish an air gap flux density of 0.5 Tesla. So how much should be the value of the coil current and the coil voltage to have this flux density in air gap 0.5 Tesla? So let me copy this. Here is the problem. We solved this kind of problems multiple times in the chapter 1. We can consider this average flux path in the core, and if we write this equation, integral of h dot dl, integral of h dot dl equal to ni, we can write, like before, h inside the core, l inside the core, plus h gap, l gap is equal to ni. So here the value of the flux density in air gap is given 0.5 Tesla. So we know that the h in the gap is a B gap divided by mu 0. We can calculate the h gap. So in this equation we have h gap. How we can calculate hc? The magnetic material is given is cast steel, and when the value of the flux density in the cast steel material is 0.5 Tesla, the value of the h is 350 approximation. Okay, so the value of the h inside the core is 350 ampere per meter. So then what is the value of the LC and L gap? The value of the L gap is given 1 millimeter. So What is the length of the flux path in the core? Is 10 plus 5, that is 15 times 4. Okay, that is 60 centimeters. The mean length of the flux path inside the core. So here in MATLAB, I considered these variables and we have this M file for the problem 3. This is the magnetic permeability of the air, the number of turns. This is B gap, desired flux density in the gap, 0.5 Tesla. The air gap length, 1 millimeter. This is the length of the average flux path in the core. The unit is centimeter. And this is the resistance of the coil. That is 4 ohms. So we can calculate the required current using this equation. If you replace the numbers, the value of the current will be 1.22 amps. Here, this is the H gap, that is B gap divided by the mu 0. This is the magnetic field intensity in air gap. The unit is ampere per meter. The value of the HC is 350 interpolated from BH curve. Yes, you can consider this curve. And here is the value of the current is H core L core times 1E minus 2 because this is in centimeter. H gap L gap times 1E minus 3 because L gap is in millimeter. Okay, is given here. So if I run the code, this will be the value of the coil current, 1.22. What is the value of the coil voltage? Yes, the coil resistance is given here, and you know that V is equal to Ri. Simply, we can calculate the required coil voltage. The value of the coil voltage is here, 4.8. So we calculated the required parameters in the first part. So let's check the numbers at the same time here for this problem. This is the part A, the value of the current and the value of the DC voltage. So determine the stored energy in the actuator system. How we can calculate the stored energy? We should use the previous equations. The stored energy in this magnetic structure is summation of the stored energy in the air gap and the stored energy in the core. Okay, so how much energy is stored in the air gap? You know that we derived the equations in the previous video. So here we have this field in the air gap. The value of the B gap is 0.5 Tesla. So the energy density in air gap is B gap to the power 2 divided by 2 times mu 0. Okay, so here we have this cross-section area of the air gap, that is the 5, right? 5, this thickness times the depth. of the problem. 5 times 5 times 1e minus 4 to calculate the cross-section area in meter square. What is the value of the volume of the air gap? Is equal to length of the gap times the cross-section area. So this is volume of the air gap. And what is the total energy, stored energy in the air gap? Is this energy density times the volume of the air gap. So in this case, we have energy in the air gap and the unit is joule. This is energy density and this is the volume of the air gap. I implemented these equations here. Okay, the energy density times the volume of the air gap. So how much is the stored energy in the core? The value of the stored energy in the core, first we should calculate the active core volume. Okay, in this problem we have these flux lines in the core. Okay, these flux lines. So what is the active volume in the core? Is this part active or not? Let me run the simulation here, analyze, to check the flux lines in the core. As you can see, this part of the core is not active. Okay, so we shouldn't consider that part in our calculations, even if I consider a higher length for this moving part. For example, here, if I consider 16 and rerun the simulation, just I want to compare the results in our calculations. So in this case, as you can see here, however, we have this volume for the core, but only this part of the stationary and the moving core is active. This is not active. We don't have flux lines in it. So when we calculate the stored energy in the core, only we should consider the active part. So how we can calculate the stored energy? The energy density is equal to integral from 0 to zero point 0.5 Tesla H dB. Okay, this equation. And this is the HP curve for this material. The HP curve for this material, we know that the energy density in the core, if we consider a uniform flux density in the core, actually we know that we don't have a uniform flux density in the core. Here you can see the distribution of the magnitude of the B inside the core. Here the B is higher than, right, these regions. But in manual calculations, we cannot consider these non-uniformities. So in this case, if we consider 0.5 Tesla inside the core, this will be the stored energy density in the core for the cast steel. How we can calculate this area? We should calculate this area numerically, okay? Because we need to have the BH curve of the material and then calculate this area numerically using MATLAB, for example. But for manual calculations, we can approximate it, right? We can approximate this, right? Consider this triangle. This is just approximation, not exact value. So consider this triangle, and what is the area of this triangle is 1 divided by 2 times zero point 0.5 Tesla times 350 Hc. So when we calculate this energy density, this one, zero point 0.5 times B gap, we consider B gap equal to B core, neglecting a fringing flux. You know that from the chapter 1. Finally, we can calculate the stored energy in the core if we multiply it by the core volume. Core volume is the length of the flux pass inside the core times the cross-section area, the active core volume. So the total stored energy in the magnetic field is the summation of the stored energy in the air gap plus the core. If I run the code here, you can see these two numbers. This is the stored energy in the core, in the air gap, and this is WF, the stored energy in the field. That is 0.38 joule. So you can see this number here. Consider our assumptions. Yes, we did this important assumption here. Okay, so now let's solve the next part of the problem. Determine the force of attraction on the actuator arm. How much force is applied on the moving part? Before answering to this part, let's review this subsection, linear system. Okay, and then answer to this part. You know, in the previous video, we derived these equations for calculation of the force. The Fm is equal to negative of partial derivative of the energy with respect to the position coordinate, or equal to partial derivative of the co-energy with respect to the position coordinate. In this problem, also, we can calculate this function, the energy as a function of distance or gap. Distance is this parameter, is the air gap. I denote it by G, the air gap thickness. Anyway, so for a constant value of the source current, we can solve the problem using this nonlinear BH curve. Find the value of the magnetic field intensities, find the amount of the energy as we did it in this part to calculate the function, and maybe we can calculate the derivative of the function, the energy function, numerically. But can we use a simpler method? Can we neglect the reluctance of the iron and solve this problem? So, you know, we have this equivalent circuit for this problem, this magnetic equivalent circuit. This is the magnetomotive force source Ni, and we have this reluctance for the iron, reluctance of the core, and this reluctance for the gap. Okay, so if we neglect the reluctance of the iron, the energy will be stored in the air gap only. So how much is the stored energy in the air gap? Is B gap to the power 2 divided by 2 times mu 0, yes, times the volume of the air gap is the cross-sectional area of the air gap times the gap thickness. So this is the energy stored in the air gap as a function of gap. So if we take the partial derivative, the force will be equal to negative B gap to the power 2 divided by 2 times mu 0 times area. Okay, so this is the force applied to the moving part. A simplification. We neglected the iron reluctance, but also we can include the effect of the iron reluctance. So in this part, the same thing is explained for the electromagnetic system of figure 3.2, the system that we studied in the previous video, this one. Okay, so the same thing is explained here in this subsection. If the reluctance of the magnetic corpus is negligible compared to that of the air gap, the flux linkage versus current relation becomes linear. For this idealized system, we can write this equation. So if you use the integral equation for calculation of the energy, integral of I d lambda, and replace the value of the current, we will have this or this equation. And if you take the partial derivative of this function, we have this equation: 1 divided by 2 I to the power 2 derivative of the inductance. Okay, so this is using the circuit element. Also for this problem, we can calculate inductance and take the derivative of the inductance. So for field quantities, again, we can do the same process, and you can prove this equation. This one, this is the force density. Okay, Newton per meter square. B gap to the power 2 divided by 2 times mu 0. If we apply this by the cross section area, we will have force. Okay, so simply we can neglect the iron reluctance. So this will be the energy stored in the air gap. We take the derivative with respect to the position coordinate. We will have this value for the force. This is the force density, and this is the area. So in our case, we can implement this equation, the absolute value. This is 0.5 Tesla to the power 2 divided by 2 times mu 0 times the area. The cross-section area that we have is 5 times the depth of the problem, that is 5 times 10 to the power minus 4. The value of the force is 248.7 Newton. Here, let's check the numbers from the right solution part of the reference. This is the value of the force that is here. Again, yes, consider that we neglected the reluctance of the iron part. What is the next part? Determine the inductance of the coil. The coil inductance is the flux linkage divided by the current, or is N, number of turns, times the core flux divided by I, N B gap, times the area divided by I. If you replace the numbers, we will have this 0.51 henries, this number that we have here. So in the MATLAB, I implemented these two equations for calculation of the force and the coil inductance. Here you can see the value of the force, and this is the value of the coil inductance. Now let's check in the ANSYS Maxwell software. Here we don't have this HB curve and we should repeat the calculations considering the HB curve that we have here. So in this case, let's change the value of the coil current to have zero point 0.5 Tesla in air gap. Okay, so I want to do it numerically. You can investigate it like before. Maybe you can export the BH curve of the material and do the calculations in MATLAB. Anyway, so here, if I add this in the middle of the air gap, this line, let's modify the coordinates. This is 10 centimeters plus gap divided by 2. This is the x. Okay, so here we have this 20 centimeters, and this is 15 centimeters or 150 millimeters. So this edge in the middle of the air gap, let me hide the region, just focus on this part. So here you can see the object that we have added, polyline 1, in the middle of the air gap. So in this case, let's clean up the previous solutions. I want to do a parametric analysis. Let's delete this parametric analysis. I want to change the value of the coil current and check when we have 0.5 Tesla in air gap. So here, do this parametric analysis. Let's change the coil current from 0 to 2 amps. The step size 0.1 amps. Yes. Run the simulation. Analyze this parametric study. So for each value of the current, we can calculate the average value of the flux density in air gap to check for what point we have 0.5 Tesla in air gap. We have a nonlinear core here, and we have this small air gap. So solutions completed. Let's create a field report. This time rectangular plot. The geometry is polyline 1. The magnitude of the B. We are going to calculate the average value of the magnitude of the B on the polyline that we created. So this is the average value. The primary sweep is the coil current. So let's check the numbers. This is the average value. Okay, I didn't save the field and mesh data, so I need to save for this post-processing. When we do post-processings on field quantities, we have to save the fields and mesh data for each simulation point, like this one. Because in this case, we are going to calculate the average value of the flux density in air gap when we change the value of the coil current. Anyway, so here is the new case, and now I can add this X marker. As you can see here, the average value of the B, the magnitude of the B in air gap is 0.5 Tesla. The current is 0.93. Okay, so we found this number using a parametric simulation. powerful ANSYS Maxwell software. So let's set the value of the coil current equal to 0.93, and I am going to calculate the force applied on this object. So we can assign a parameter force calculation. So here is the parameter that we defined. We are going to calculate the force applied to this object. Yes, for this value of the current that we found. So let's clean up the solutions again and run the analyze. So what will be the result? What do you think? In this case, we have this field, and now I can show the value of the force. We have this moving part, so the force will be applied in x direction, fx, and in y direction, fy. Okay, because here, as you can see, we have this contact and we have a holding force in the negative y direction also. Okay, so we calculated fx in the right problem, this parameter. So in this case, let's plot the field reports, the polyline 1, magnitude of the B. What is the average value? Is this is millitesla or zero point 0.5 Tesla. If we change the unit here, 0.5. In this case, the magnetostatic report data table, the force X and Y. The force X, again, we should multiply it by the distance, right? The depth of the problem, 5 centimeter divided by 1 meter, because the depth of the problem by default is 1 meter. Okay, this is the value of the force Fx. And what is the Fy? At trace is equal to this one. Perfect. Okay, so yes, this is the number that we calculated, neglecting the energy in the core, neglecting the reluctance of the iron. And this is what we calculated in ANSYS Maxwell. Our assumption, right, is good. This is the value of the force in x direction, and this is the value of the force in the y direction, the holding force, because we have a contact here also. How I can estimate this one, this force? Again, let's draw a line here, or let me do this. Select mode object, this object, hide, and also delete the plots. Selection mode, let's select this edge. From here, create object from edge, this one. Now I am going to, let's show this object. I am going to plot the magnitude of the B for this edge also. Let's clean up the solutions and run the analysis setup again. I want to investigate this equation. Can we calculate Fy using this equation or not? Is equal to B to the power 2 divided by 2 times mu 0 times the area. Okay, so solution completed. Let's select polyline, the new one, new report. This is the value of the magnitude of the force. Let's calculate the average value. is 0.57. The average value of the force along this edge. So let me plot B vectors on it. You can see B vectors here. Also, you can check the actually this parameter, other edge force density, surface force density. Anyway, so how much is the force? Minus 319. This is the average value of the flux density, 0.5716. So here I write 0.5796 to the power 2 divided by 2 times mu 0 times, this is the area of the gap, this number, yes, 334, close to this number. Yes, in this case, we actually consider this portion of the material, but we need to consider this line. Okay, this line, just I consider this contact. As we did in air gap, also we consider this contact between these two parts. So this is an important concept. This is an important concept, also known as the Maxwell stress tensor, right? These methods should result in the same value of the force or torque. Yes, we used the equation presented in this subsection to calculate the force for this problem using an idealized case, neglecting the reluctance of the core. An important equation, this is the force density. And also we have this value for the coil inductance. Yes, is not too complex. You can review the calculations. Now let's solve the part B. The actuator arm is allowed to move and finally the air gap closes. I for 0 air gap, determine the flux density in the core, force on the arm, and stored energy in the actuator system. Again, we can write this equation. Ni is H core L core plus H gap L gap. The length of the air gap in this case is 0. And we have this equation. So what is the value of the H inside the core is equal to this number, around 1000 ampere per meter. So for this value of the H, 1000, the value of the B will be 1.2 Tesla. Okay, this number. So in this case, we have B core. Again, we can calculate the force using this important equation, B to the power 2, 2 times mu 0 times the cross-section area. That is this one. Okay, 1432. This number that we have here. Let's check the solutions for this problem. This value of the force. This is the value of the B. Okay, the flux density, that is 1.2 Tesla. So how much is the stored energy in the magnetic field in this case? In this case, again, we can use integration. The value of the flux density in the core is 1.2 Tesla. This number, yes. And this is the value of the H. How much is the stored energy in the magnetic field? Is the area of this region. This is the energy density. We should multiply it by the volume of the core. Again, if we have the HP curve data, we can calculate this area numerically, but also we can approximate it using this triangle, using an approximation method. In the problem, right, it should be mentioned that we should use approximate method for calculation of the stored energy. So in this case, the energy density is equal to 1 divided by 2, 1.2 Tesla times 1000, okay, for the H. So if you calculate this and time this by the volume of the core, you can calculate the stored energy. So here are calculations for the part B. This is the value of the HC for the part B. This is the flux density, interpolated flux density, interpolated from BH curve. The unit is Tesla. This is the magnetic field intensity in the core, ampere per meter. And this is the value of the force. This is the energy stored in the core. The unit is joule. This product times the volume of the core. So here, if I run the code, you can see these numbers. This is H, this is B, and this is the force. This is the stored energy, 0.91. This number, 0.9 joule. So for this problem, let's do the same. If we set the value of the air gap equal to 0, let's repeat the analysis. So we close the air gap and then we calculate the force again. Here, the value of the flux density, the average value of the flux density in the core is 1.45 Tesla. Yes, in this problem, the material is different, okay, than what we have in the problem. Here I used this material, magnetic alloy, silicon core iron. In this case, what is the value of the force when the air gap is 0? Yes, as you can see, the value of the force for the x and y directions are the same, minus 2.1 kilonewton. Let's check, 1.45 Tesla. I am going to use the same equation here, 1.45, 2.1 kilonewton. Okay, perfect. So you can use this powerful software to calculate the force. Also, you can calculate the force manually, compare your numbers. We have these two air gaps. This air gap is closed, yes, even when we change this number, for example, 2 millimeter. This air gap is always closed. We have one element of the force here and one here on this moving part. Yes, you have to repeat the same calculations in ANSYS Maxwell. Maybe you can change the parameters to learn this important concept, okay, and this important equation. So now let's solve the next part. Determine the energy transfer, excluding energy loss in the coil resistance between the DC source and actuator. Assume that the arm moved slowly So the value of the current, right, remains constant considering this condition. What is the direction of the energy flow? How much mechanical energy is produced? So for the first case, the air gap, for the case 1, the air gap thickness was 1 millimeter. For the case 2, the air gap is 0, is closed. Yes, the air gap is closed. We have this equation, dWe is equal to dWf plus dW mechanical. So, what is the value of the dWe in this case? dWe is I d lambda. This is actually this case when the movement occurs very slowly and the current remains constant, this case. So the area of this rectangle is dWe. Okay, so dWe is I d lambda, or this is actually I times, what is the flux linkage? N A times the change in the value of the B. This is B for the second case minus B for the first case. For the first case, it was zero point 0.5 Tesla. For the second case, it was 1.2 Tesla. We have A, we have N, we have current. We can calculate dWe. Also, we calculated the stored energy in the magnetic field. For both cases, dWf is Wf new minus Wf old. Finally, we can calculate dWm. Here you can see calculations in the M file. This is dWe. This is dWf. Wf calculated for the new case. This is for the old case. When we have the gap, this is dWm, the mechanical. So what is the value of dWm? 0.53. In the reference, let's check the numbers. Here we have this number, 0.54 kilos. Okay, so this is dWe. The value of the dWe is 1.06. 1.06 joule. Source to actuator, and this is the change in the mechanical energy. Perfect, perfect. You can do these calculations, okay, to solve this problem. How we can calculate the energy in the ANSYS Maxwell? And let me do this practice, an important one. So let's clear our reports. And here I am going to do this parametric analysis. I am going to set the value of the current constant, and I am going to change the value of the air gap thickness. So here in optimetrics, let's change the value of the air gap from 0.5 to 2. The step size 0.1. Okay, so options, save, field, and mesh. In the previous solutions, in this case, I am going to fix the value of the current and change the value of the air gap thickness. So then we calculate the energy. So let's analyze this parametric analysis to change the value of the air gap thickness. I am going to calculate this function numerically in the software. The energy as a function of the gap, this function. So simulations completed. How we can calculate the energy in Maxwell 2D fields calculator? Let's select this parameter, quantity, energy, okay? And let's select all surface objects, calculate the integral. Yes, the integral of the energy over all of these surface objects. So this is, let's write WF energy, and here let me plot this variable, this output variable that we defined from the field report, this parameter, the energy as a function of the gap. So is this number correct or not? We should first modify it by the depth of the problem. So 5 centimeter divided by 1 meter. Apply. This is the right value of the energy. Now let's calculate the co-energy variation versus the air gap. So again, from Maxwell 2D calculator, this time we can select the co-energy. Consider that this is the co-energy density, and because we are solving a 2D problem, this is the joule per meter square. Okay, so this is why I calculate the integral. So this is co-energy. We select all surface objects and calculate the integral. So this is the total co-energy for the problem. Again, we can plot the co-energy modified by the depth of the problem. In this case, as you can see here, the energy and co-energy are the same because we don't have a deep saturation in the problem. But when we have deep saturation, the value of the energy and co-energy are different. So this is the case. For example, suppose we have this current, this is the flux linkage, and this is the HB curve. So when the level of the excitation is low, the value of the energy and co-energy, right, are the same. But when we have deep saturation, we will have different values. Now let's investigate this equation. The energy plus co-energy WF prime must be equal to flux linkage times current. So here, what is the value of the flux linkage? Let me check the rectangular plot. This is the flux linkage times 5 centimeter divided by 1 meter. We need modify them by the depth of the problem. Meter times the coil current. So here is the curve. Now if I sum up the co-energy plus energy, yes, the co-energy plus the energy, here just we need to do this, right, summation. This is energy and co-energy. Now you can drag and drop this on this axis to compare. As you can see, yes, in this figure we have these two, right, quantities, the summation of the energy and co-energy, and this is lambda I close to each other. Yes, we have some numerical right? Noises, but these two are the same. How we can calculate the force? So let's plot the value of the force Fx times 5 centimeters divided by 1 meter as a function of the gap. So can we calculate the force using energy definitions or not? In this simulation, we considered the value of the coil current constant and we changed the air gap thickness. Okay, so let's check the reference here. We have these two equations, right, for calculation of the force. This is the co-energy. In the co-energy method, we take the partial derivative of the co-energy with respect to the position variable, where the value of the current is constant. And in the energy method, we calculate the partial derivative, the negative one, when the flux is constant. In this parametric study, the flux is not constant, is varying, but the value of the current is constant. So here I use the co-energy and I take its derivative. So this is the co-energy. We can use the derivative function here. Derivative. So let's multiply by this. And this is the value of the force calculated by the derivative of the co-energy. And this is the force calculated by the software. So let's drag this and put it on this axis. Then you can compare. Both results generate the same curve. So here you need to add this X marker when the value of the gap is 1 millimeter. We have these two values. You need to reduce the step size. Okay, this is just a derivative calculation. Don't worry about this. Okay, so as you can see here, we calculated the force using the co-energy formulation Y because the current is constant, and we did a constant current parametric simulation and compared the force that is calculated by ANSYS Maxwell. So both results, right, are the same. So you can repeat this analysis. Even you can calculate these energy and co-energy functions. You can export the BH curve of the material to MATLAB and calculate the area numerically and calculate the force. Okay, so anyway, I think it's enough for this video. You can repeat solving this problem and let's continue in the next video.